Have you ever wondered why we can't fly an airplane into space? This is a question that might have crossed your mind at some point. It's an intriguing thought, isn't it? The idea of soaring into the cosmos in a conventional airplane like the ones we see at the airport. But, as with many things in life, there's more to it than meets the eye. There are several reasons why this isn't possible, and today, we're going to explore them. Firstly, it's all about aerodynamics. This is the science that deals with the motion of air and the way that it interacts with objects in motion, like our airplanes. Now, airplanes are designed to take advantage of the Earth's atmosphere. They generate lift, the upward force that opposes gravity and keeps the plane airborne, by moving air over their wings. Imagine it like this. The wings of an airplane are designed in such a way that they push air down towards the ground, and in response, the air pushes the airplane up, enabling it to fly. This is a beautiful dance based on the principle of action and reaction that Sir Isaac Newton defined centuries ago. However, as an airplane ascends, the atmosphere gradually thins out. The air becomes less dense, and there's less of it to push against the wings. Consequently, the lift generated by the airplane decreases. Eventually, as we approach the edge of the atmosphere, the air becomes so thin that it's almost non-existent. There's simply not enough air left to generate any significant lift. And here's the crux of the matter. Without an atmosphere, our conventional airplanes are rendered powerless. They can't generate the necessary lift to keep them airborne, and they certainly can't climb any further. So, without an atmosphere, airplanes simply can't fly. The second reason is the limitations of airplane engines. Now, let's delve into the fascinating world of aviation engineering. Jet engines, like those found on commercial airplanes, are marvels of modern technology. They're powerful, efficient, and reliable. But they have one major limitation. They require oxygen from the atmosphere to combust fuel. Picture it this way. The jet engines on an airplane are like a roaring campfire. The firewood is the fuel, and the oxygen in the air is what helps the fire to keep burning. Without enough oxygen, the fire would fizzle out. Similarly, jet engines suck in huge amounts of air, mix it with fuel, and ignite it. This combustion process generates the thrust that propels the airplane forward. But what if we take our airplane, with its air-breathing engines, beyond the Earth's atmosphere, into the vacuum of space? Well, just as a campfire would struggle without air, so too would our airplane's engines. In the vacuum of space, there's no air, no oxygen for the engines to use for combustion. The engines would fail, and our airplane would find itself in a bit of a predicament. So while jet engines are perfectly suited for propelling airplanes through the Earth's atmosphere, they hit a wall, so to speak, when it comes to space travel. In other words, airplane engines aren't built for space travel. The third factor is the need for speed, or more precisely, escape velocity. Now, you're probably wondering, what is escape velocity? Well, it's the speed that an object needs to reach to overcome the gravitational pull of a planet or a moon. In the case of Earth, this velocity is approximately 25,000 miles per hour. That's about 33 times the speed of sound. But why is this speed so important? You see, to reach space and stay there, an object has to move fast enough so that it falls towards Earth, but also moves forward far enough that Earth curves away underneath it. It's a bit like throwing a ball so hard that it keeps missing the ground. That's what we call an orbit. Now, consider our airplanes. The fastest commercial airplane, the Concorde, could reach speeds of just over 1,300 miles per hour. That's impressive, but it's nowhere near the speed necessary to reach space. Even military jets, which are much faster than commercial airplanes, cannot come close to the required escape velocity. Our airplanes are marvels of engineering, capable of taking us across continents and oceans in a matter of hours. However, they are designed for the atmosphere, not the vacuum of space. Their engines, their wings, their materials, all are optimized for flight within Earth's atmosphere. Unfortunately, our airplanes just aren't fast enough to break free from Earth's gravitational pull. The final hurdle is dealing with thermal issues. As we venture beyond our atmospheric cocoon, we encounter a realm of extremes. In the void of space, the temperature can fluctuate wildly, presenting a unique challenge for any would-be space traveler. In the shadow of a spacecraft, temperatures can plummet to the bone-chilling cold of -275 degrees Fahrenheit. That's colder than any natural temperature recorded on Earth. On the flip side, when directly exposed to sunlight without the filtering effect of our atmosphere, temperatures can soar to a scorching 250 degrees Fahrenheit. This drastic range, from extreme cold to intense heat, poses a significant challenge. Airplanes, which are designed to operate within the relatively mild and stable conditions of Earth's lower atmosphere, are simply not built to handle such temperature differentials. The materials used in aircraft construction, from the aluminum skin to the rubber tires, would either freeze and become brittle in the extreme cold or melt and degrade under the intense heat. The thermal protection systems that allow spacecraft to endure these conditions are complex and heavy, not something that could be easily added to a commercial airplane. So, while it's a fascinating idea, flying an airplane into space is currently beyond our reach. So, there we have it. We've explored why a standard airplane can't fly into space. We've delved into the crucial role of aerodynamics and how the atmosphere's thinning with increased altitude impacts lift. We've discussed the limitations of air-breathing jet engines, which require oxygen to function. We've faced the daunting necessity for escape velocity, a speed far beyond what any commercial aircraft can reach. And we've tackled the thermal challenges that come with space's extreme temperatures. Thanks for joining us on this journey of discovery. Stay curious and keep exploring.